Hello and welcome to another lecture about data structure. Today we will discuss about queue, a linear data structure in which operations follow specific order. First in, first out is the specific order that is the main structure of the queue. There are mainly 6 operations to perform different actions on the queue. Initially we have 2 pointers and we will discuss about them later on this video. The first main operation that we're going to discuss about is enqueue. Enqueue adds element at the rear of the queue. The next one is dequeue. Dequeue removes elements from the front of the queue and in fact removes the frontmost or oldest element in the queue. Is empty returns true if the queue is empty, and is full returns true if the queue is full. Sometimes when the queue has reached to its allocated capacity, then adding elements is not possible. Pick returns the value of the front of the queue, and we can get that element. And finally, size returns the number of the items within the queue. So let's have a closer look at our illustration. Initially, we have 2 pointers, rear and front. Rear tracks the newest inserted element, and front will track the oldest inserted elements. So the first operation is enqueue that adds elements to queue. We are only allowed to add items from rear and remove items from front. Let's to see how dequeue works. As discussed earlier, removing is only possible from the front of the queue. To just explain it in detail, we need to talk about 2 methods. One is to remove the elements at the front position and then move other elements 1 position forward. Or in other words, we need to shift elements, and in this approach there is an overhead because every time that we remove an item, then we need to shift all elements 1 position. So let's to have a quick pause on what we have on the screen and show you another method. As is observed in this method, we remove the element from the front of the queue, and instead of shifting all elements, we only need to move the front pointer to the next element. However, this approach will reduce the capacity of the queue by 1 space each time. The next operation is empty, and surely it returns false because we have items there in our queue. And the next operation is full, and it returns false because we can still put items there in our queue. The next operation is pick that will return the oldest item, or in other words, it will return the value of the front of the queue. And finally, size will return the number of items in our queue that is equal to 3. In fact, it returns the number of elements present in a queue container. The introduction section, we covered simple queue so far. As is observed, a circular queue is a specific data structure that all elements are represented as a circular. So initially the queue is full, and let's to have an empty one and start from the beginning. We have initially 2 pointers that they indicate to -1, and that means the queue is empty. As you can see, just as a simple queue or a linear queue that we covered in introduction section, it seems that we are incrementing rear to find the next position of the next element to insert into our queue. Let's do it until the end of the queue. And now let's to perform dequeue and remove some of elements there. Just as a simple queue, it seems that we are incrementing front pointer to remove elements. Therefore, now let's have a closer look at simple queue. This is a simple queue, and initially the queue is empty. But let's to add some elements. Initially we have set front and rear to -1, and it indicates that the queue is empty. Then we add an element, and those pointers indicate to the first added element, since we have only 1 element there. And then for adding new elements, we need to only increment rear. As you can see, the rear is incrementing to add new items. And now let's remove 1 item. This part is very important. Suppose once you remove an element, you have a non-usable space. The question is how to use this space efficiently. If we increment the rear pointer, then the next index would be 4. That is not possible. So this is exactly why circular queue is introduced to overcome this limitation. Instead of incrementing rear, we use this formula to add an element in the location that is possible. For instance, look at index 7 and look at index 0. It indicates that we have an empty space there to add new element. The only thing that we need to do is to access index 0 in order to add new element. So use the formula, and 7 plus 1 is equal to 8, and 8 mod 8 is equal to 0. This is the way that we can access that index. And simply you can add new element. And now just remove all items in the first round. And this is another benefit of circular queue. That is how we can access the first index to remove that element. The formula is the same, and we only need to add 1 to 7, that is equal to 8, and 8 mod 8 is equal to 0. And now we can access to element at index 0. Now let's to have another example to add new item. Rear is equal to 0. So 0 plus 1 is equal to 1. 1 mod 8 is equal to 1. That's all about circular queue and its advantages over simple queue. Another type of queue is doubly ended queue. Also, we can call it dequeue. This type of data structure does not follow the principle of first in, first out rule because we can add or remove items from both sides. For adding elements, we can increment rear as you can see, or decrementing front to add new elements. And just for removing items, we can decrement rear to remove an item from right side, or incrementing front to remove items from left side. Decrement rear to remove an item, or increment front to remove an item from the other side. The last type of queue that we will discuss about is priority queue. First, we need to talk about their characteristics. Each item is associated with a priority, and items are ordered by their key values. There are two types of priority queue: ascending order priority and descending order priority. This priority queue will arrange elements in their ascending or descending order. In this example, we have 4 elements with descending order. It means the element with largest value has the highest priority. So in this case, we must treat 90 as the highest priority. As you have noticed earlier, our queue has 2 elements with the same value or the same priority. In this special case, if 2 elements share the same priority, then the queue follows first in, first out principle. You can implement priority queue in one of the following ways: binary heap, linked list, arrays, and binary search trees. Binary heap is preferred since it is the most efficient way to implement priority queue. Hello and welcome to the next lecture. Today we will discuss about stack, a linear data structure in which operations follow a specific order. This specific order is based on a last in, first out data structure. In a nutshell, removing or adding an item is only allowed on top of the stack, and any object can be accessed only from the top of the stack. There are mainly 6 operations to perform different actions on the stack. Push is capable to add an item to the top of the stack. Pop can remove an item from the top of the stack. Is empty checks and returns true if the stack is empty. Is full checks the stack and returns true if the stack is full. And in fact, when the size of the stack has reached to its maximum allocated capacity, then this function will return true. Pick returns the value of the last inserted item, and lastly, size returns the number of items in the stack. So now let's have a closer look at these operations. First, let's see what push is exactly. Push will add elements on top of each other. We add 5 items. The next operation is pop. Pop will remove an element on the top of the stack. In fact, last inserted element will be removed. So when we want to remove 40, before that we must remove 50. So we remove 50, then we are allowed to remove 40. IsEmpty is the next operation, and it will check if the stack is empty. And for now it will return false since we have items in our stack. IsFull will check if the stack has reached to its maximum capacity, and for now it will also return false because we can still add items. Pick will return the value of the last inserted item that is equal to 30. And finally size will return the number of items in our stack. Hello and welcome to the lecture about linked list. In this lecture, we're going to discuss about linked list, a linear data structure that consists of series of nodes connected together as chain. The simplest and most common one is called singly linked list, in which each node has a data and a pointer to the next node. This part holds the data and this part is the pointer and points to the next node in the list. At the beginning of linked list, there is head. Head doesn't contain any data. Head contains the address of the first node in the linked list. And then each node also has the address of the next node in the list. Last node always indicates to the null, but note that null is not a node. The next type of linked list is called doubly linked list. As you can remember, in the singly linked list, each node has a pointer to its next node. However, in the doubly linked list, each node has also the address of its previous node. This is only the big difference. And the next type is called circular linked list, which can be either singly linked or doubly linked. The big difference is that there is no null in this structure. The pointer of the last node will indicate to first node instead of indicating to the null. In a nutshell, we can say that there is a link between the last item and the first item. And doubly linked, all nodes have pointers to the next and previous items. Additionally, the last node indicates to the first node and the first node indicates to the last node. This was all about introduction to linked list. Let's have a closer look at deletion and insertion. Let's get started by deletion operation. Suppose we want to delete the node in the middle. The only thing that you need to do is to traverse to element just before the node that you want to be deleted. So in this example, if you want to remove the second element, you should traverse to the first element and change its pointer. Change pointer to exclude the node from the chain. Let's see another example. This time, suppose we're going to delete first node. The only thing that we need to do is to change head pointer to point to the second node, which is last one here. And for insertion operation, suppose we want to add a node at the beginning of the linked list just after head. The only thing that we need to do is to allocate memory for the new node and store data, then change the pointer of the head to point to the new node and change the pointer of the new node to indicate to the next node. Let's see another example. Again, allocate memory to store the node, then change the pointer of its previous node to indicate to the new node and change the pointer of the new node to the next item in the list. Hello and welcome to another lecture about data structure. Today we will discuss about graph theory. First, what is exactly a vertex? A vertex or node is the fundamental unit of a graph as well as edge. However, edges are responsible to connect these vertices. So now what is a graph? A graph is a nonlinear data structure that consists of a set of vertices and edges. And as you can see, sets of vertices are connected via edges. Now let's discuss about type of graphs. The first is undirected graph, a set of vertices and edges in which the edges have no orientation. So it means that AB is identical to BA, and it doesn't matter whether we call it AB or BA. The next one is directed graph. Directed graph is a graph in which the edges have orientation. So AB is not identical to BA. For example, there's only one path from A to B, but there isn't any path from B to A. And this is the same for example, A to C. For the next vertex, which is B, there is no path to its adjacent vertices. And for D, there is only two paths from D to B and D to C. For E, there is only one path to D. And finally, for C, there's no path to its adjacent vertices. The next type is weighted graph, and in this type, every single edge is associated with a value in the graph. The next one is directed acyclic graph, that is a directed graph but with no cycle in the graph. A cycle is a path that the starting vertex and ending vertex is the same. Or in other words, the last and first node are equal. Let's have a closer look into another example. Suppose we're given this graph. If we can find a path that the first vertex and the last vertex are the same, then we can say that there is a cycle in our graph. Let's start from A and then it points to the B, and from B let's go to the C, and then C points to the A. Because the first node is met again, then we say there is a cycle in graph. The next type is multigraph. A multigraph is an undirected graph in which multiple edges or loops are allowed. So what is exactly a multiple edge? A multiple edge or parallel edges are two or more edges that connect the same two vertices. In this example, vertex A and vertex C are connected with two edges. So there's also a loop in our illustration. A loop is an edge that connects a vertex to itself, just as is observed for vertex B. The next one is simple graph. So a simple graph is a kind of undirected graph in which multiple edges and loops are not allowed. The next type is connected graph. In a connected graph, there is a path between every pair of vertices. So it means that, for example, let's to see if there is a path between B and other vertices. As is observed, there is a path from B to A and from B to D. And also there is a path from B to E that goes from D. And a path from B to C, which goes from D or A. In a nutshell, there is a path from B to every other vertices, whether direct path or indirect path. So if all other vertices satisfy this condition, then we can say that the graph is connected. And in this case, because there is a path from every vertex to every other vertex, then we can say this graph is connected. The next one is completed graph. In connected graph, we talked about path between every pair of vertices, but here in completed graph, we will discuss about edge between every pair of vertices. It means there is an edge from every vertex to every other vertex. This graph is not completed, but let's to see if it was completed. Let's start from vertex E, then we must have edges to other vertices. If we want to have a complete graph, we must check each vertex, then create an edge between other vertices as is shown. Do the same process for other vertices in order to have a completed graph. Now the graph is completed. Hello and welcome to another lecture about graph theory. In this lecture, we will discuss about graph representation. The first way in which the graph is represented is adjacency matrix. It is a square matrix used to represent a finite graph. This is a Boolean structure and checks if two vertices are adjacent. We assign 1 if there is an edge between two vertices, otherwise we assign 0 that it means there is no edge. Rows represent for source vertices and columns represent for destination vertices. Let's to have a closer look and start by a vertex. Vertex A. There is only one edge between A and C. Loops are not allowed, so from A to A is 0. From A to B is also 0 because there is no edge, and from A to C is 1 because there is one edge between them. And A to D is also 0 because there is no edge between A and D that directly connect them. The next one is B, and the only adjacent vertex is D because there is only one edge between them. The next vertex is C. As is observed, from C there are two edges that connect C to D and C to A. So CA and CD is 1 and the rest is 0. The next vertex is D, and from D there are two edges that connect D to B and D to C. So adjacent vertices are B and C. There's also another way for graph representation, that is adjacency list. In this method, every vertex stores the list of adjacent vertices. We use linked list to construct this list. Let's start by our illustration and start from vertex A. There's only one vertex, that is C. The adjacent vertex is C. The next one is B, and the only adjacent vertex is D. And the next one is C, and the adjacent vertices are A and D. And the last one is D, and its surrounding vertices are B and C. Hello and welcome to the lecture about spanning and minimum spanning tree. Spanning tree is a subgraph of an undirected connected graph. It has some conditions that must be met. The graph must be undirected and connected. A spanning tree must contain all vertices with minimum possible number of edges without any cycle. So let's have a closer look and see how we can construct some spanning tree from our main graph with minimum possible edges but containing all vertices. This is one of the possible spanning trees, and you can see other possible illustrations of the spanning tree from our main graph. Each of them contains all vertices with minimum possible edges. Now, what is exactly the minimum spanning tree? A minimum spanning tree is a tree of minimum total weight and must contain all vertices with minimum possible edges. And there must be no cycle. So let's just see how many spanning tree we can create from our main graph. This is one possible spanning tree, and the sum of edges is 14. This is also another spanning tree that sum of edges is equal to 8. And the next spanning tree and the sum of edges is equal to 15. And the last possible spanning tree that the sum of edges is equal to 17. And among all spanning trees, the tree with the minimum total weight is our minimum spanning tree. Hello and welcome to the lecture about Kruskal algorithm. That is a way to find minimum spanning tree from a graph that includes every vertex where the total weight of all edges in the tree is minimized. First, we have some conditions for the graph. The graph must be connected, undirected, and weighted. And the next condition is that the parallel edges or self-loops are not allowed. Additionally, we must discuss about minimum spanning tree conditions. The first one is that no cycle is allowed in minimum spanning tree. The second one is that the minimum spanning tree contains all vertices. So let's dive into an example. Suppose we are given this graph. The first step that you need to take is to sort all edges in non-decreasing order of their weight value. And now this is the time to pick the smaller edge among all until there is no cycle. The first edge that we're going to choose is EC that connects two nodes. The next one is AB and there is still no cycle. Then DC, but adding ED will form a cycle and is not allowed. The next possible edge that we can add is EA, but adding edge between C and B is not possible because it forms a cycle. So we can conclude that adding the edge between DE or adding the edge between BC is not possible anymore because they form a cycle. Hello and welcome to the lecture about Prim's algorithm. Prim's algorithm is a greedy algorithm that finds minimum spanning tree where the total weight of all edges in the tree is minimized. There are conditions corresponding to original graph. The first one is that the graph must be connected, undirected, and weighted. Additionally, parallel edges and self-loops are not allowed. Also, there are some conditions related to the minimum spanning tree. There must be no cycle in the minimum spanning tree, and the minimum spanning tree must contains all vertices. So let's dive into an example. Suppose we're given this graph. Step 1 is to initialize the minimum spanning tree with an arbitrary vertex. I choose node E randomly. Step 2 is to add next vertex with the minimum possible edge connected to the node E. There are 3 nodes that they are connected to the node E with 3 edges. However, the least weight value is the edge between C and E. In the next step, find the minimum edge regarding all edges connected to E and C. There are 3 possible nodes and 4 edges. Minimum possible edge is between E and D with a weight value of 3. Repeat previous steps, but be careful to not form a cycle in each step. You can suppose that we treat E, C, and D as a single node and we must add the minimum edge that is remaining. Now there are 3 possible edges. As you probably noticed, adding edge between C and D forms a cycle and is not allowed. Choose edge between E and A that has less weight value. Finally, last vertex will be added by minimum possible edge. Last minimum weight value is between A and B with a value of 2. Adding more edges will form a cycle, so stop here and the minimum spanning tree is completed. Maybe you have noticed that a special case can happen when we have more than one edge with the same weight value. Suppose that the weight value between D and C is 3, just as the same as between E and D. Pick the edge between ED or DC randomly and move on until there is no cycle. Hello and welcome to another lecture about data structure, and specifically today we're going to discuss about graph traversal, and this refers to the process of visiting each vertex in the graph. There are two types of graph traversal, and we're going to start by depth first search. In this approach, we use a stack to remember and track vertices that we're going to visit. All adjacent vertices are pushed into stack, and if there is no vertex to visit, then visited vertices are popped. So let's get started by an example. Suppose we are given this graph. The first task is to pick a starting node. This is totally up to you, and you can pick any node you would like. So I prefer to start by node B. Additionally, we put node B in visited list and then put all its adjacent vertices into stack. Its adjacent nodes are A and D. Again, it's up to you, and it doesn't matter which one you select first to put into stack. So I prefer to add D and then A to the stack. As is observed, these two nodes are the only adjacent nodes of B. Then we must put them into visited list. Please note that we always add or pop an item from the top of the stack. Regarding this important point, we must consider node A first. So A will be marked as visited and then put it into visited list, and we must add all its adjacent into stack. Therefore, node C is the only adjacent to node A, and add it to the stack. Node C has no adjacent, therefore mark C as visited and put it in the visited list. Now, as is observed, there is no unvisited adjacent node. In order to be able to traverse the graph to check if any adjacent node is remained, we must pop the last item, pop C, and as you can remember, A was visited and A is in visited list. Then pop A. When we reach to the node D, then we can add it into the visited list. Additionally, put its adjacent nodes into the stack. Node E is the only adjacent to the node D, so mark it as visited and add its adjacent into the stack. Node F is the only adjacent to node E. There's no adjacent node, so mark F as visited. Now there's no unvisited adjacent node, so remove items from stack to check if there are any unvisited nodes. All nodes are visited and the stack is empty now. Now let's check what is breadth first search. The process is a little bit different because we're going to use queue instead of stack that we used for depth first search. Again, choose any node you would like. It's totally up to you that which node is selected first. Select a node and put it in the visited list. Initially, I choose node B and put it in the visited list and put all its adjacent nodes in the queue. Its adjacent nodes are A and D, and it doesn't matter which one you select to put in the queue first. So initially, I insert A and then insert D into the queue. It means when we're going to process nodes, then we must start from the one that is at the front of the list, which is A here. Mark node A as visited and put its JSON nodes into the queue. Node A will be placed into the visited list. C is the only adjacent node to the A. Then we are going to process the next element, that is node D, and put its adjacent node into the queue, that is node E. So process the first element, that is node D, and put it in the visited list. The next node that we're going to mark as visited is C, and it doesn't have any adjacent node. Put node C into the visited list, then process the next node, that is node E, and put its adjacent nodes into the queue. Its adjacent node is F. Put E into the visited list and finally mark F as visited and put it in the visited list. Now the stack is empty and we are done. Hello and welcome to another lecture about data structure. In this lecture, we will discuss about trees. First, we will start by node. What is a node or vertex? It is in fact an entity that contains a key or a value. Moreover, a node usually has a link or pointer to its child nodes that we will call it edge. Let's do have a tree with some nodes and edges. Root node is the topmost node of a tree. And internal nodes are any nodes of a tree that has child nodes. And the node without any child nodes are called leaf nodes or external nodes, just as is shown in the illustration. The height of a node is the number of edges from the node to the deepest node. For instance, suppose we want to achieve the height of the node with a value of 18. Then, as is observed, the deepest nodes are the node with a value of 4 and 11. However, we only need one of them because both of them share the same level. Therefore, the number of edges are 2, or in other words, the height of the node with a value of 18 is equal to 2. And now, what is the depth of the node? The depth is the number of edges from the root to the desired node. Suppose we're going to calculate the depth of the node with a value of 4. Then, as you can see, the number of edges from the root node, which has the value of 20, is equal to 3. Or in other words, the depth of the node with a value of 4 is 3. Now, what is tree traversal? Traversing is the process of visiting each node in the tree. For instance, finding the largest element or traversing in order to add or remove a node. For all these operations, you need to visit each node. There must be a specific way to this end, and you will learn that in a lecture which is about tree traversal, and specifically I have explained all details about pre-order, in-order, and post-order traversal. Hello and welcome to the next lecture. In this lecture, we're going to talk about tree traversal. Traversing is the process of visiting each node in the tree for different purposes. There are mainly 3 ways, and first we will start by pre-order traversal. In pre-order traversal, always note that we must start from the root node, and this is why we call it pre-order. Because the root is visited first, then visiting the left node or left subtree, and then visiting the right node or right subtree. Initially, we create a list for root node, for left node, and for right node. We call it root, left, right. Let's get started by our illustration. First, we need to visit the root. The root has the value of 20, so put 20 in the root list. Then go and visit left node. However, we do not have a node, but also we have a subtree on the left side. Go ahead and start off the process again and start from the beginning for the left subtree. Find the root the root has the value of 18 and put that in the new root list. Then go to visit left node, but again we have a subtree, so start off again and find the root and put it into the root list, and then put 10 into the root list. This time we have only one node on the left side and one node on the right side, so put them into the left and right list. Then step backward and put all of these values in the left list of previous step. And now the root and left list has completed, but we need to fill the right list and we have to put the node with the value of 14 into the right list. Now traversing the left subtree is completed. Therefore, step backward and put all these values into the left list of the first step. And now it's the time to traverse right subtree. On the right, first visit root and put it into the root list. Then put 6 in the left list and 24 into the right list. Step backward and put all these elements together into the right list of the previous step. We are done with pre-order traversing, and as you can see, all nodes are marked as visited with a specific order. Let's move on and talk about in-order traversal, in which the root is in the middle. Simply put, I mean we visit left node first, then a root node, and then right node. Let's suppose we're given this tree. Initially, we must visit left node, but we have a subtree on the left side, so continue until you find the first left node. Again, we have a left subtree, but now we have reached to the first left node. Put the node with the value of 4 into the left list, and then put root node with the value of 10 into the root list, and finally put the node with the value of 11 into the right list. This list corresponds to the left list of the previous step. So put all these elements together into the left list of previous step. Now we must fill a root list. Put the node with the value of 18 into the root list and put 14 into the right list. Then put all these values into the left list of previous step as is shown. Now put 20 as the root node into the root list and traverse the right subtree. As is observed, we have a subtree on the right side, so put the node with the value of 6 into the left list and 8 into the root list and 24 into the right list. And put all these elements together into the right list of the previous step. Now we are done with in-order traversal. This was all about all necessary steps to do. Always note that we must traverse left node, then root node, then right node. Let's move on and discuss about post order. We call it post order because the root node is visited last. In a nutshell, we must visit left node, then right node, and lastly root node. Let's get started by our illustration. Find left node. Instead of a node, there is a subtree on the left side. Therefore, create another list to traverse this new subtree separately. However, again on the left side we have another subtree, so create another list to traverse it. And finally, we have just reached to the first left node. Put that in the left list. And then put the right node with the value of 11 into the right list, and finally put the node with the value of 10 into the root list. Additionally, put all these elements into the left list of the previous step, which corresponds to. And then traverse the right node of the first subtree by putting node with the value of 14 into the right list and the node with the value of 18 into the root list. And again, put all these elements together into the left list of the first step and continue to traverse the remaining elements. As is observed, On the right side, we have a subtree. So that's to have another group of lists to handle this situation. Then start the process by putting node with the value of 6 into the left list and 24 into the right list and 8 into the root list. And put all these elements together into the right list of the previous step. And finally, the last element that we put in our list is the root node with the value of 20. We are done and the post order is achieved by traversing the tree. Hello and welcome to another lecture about data structure. In this lecture, we are going to talk about different type of binary trees. In a binary tree, each parent can have at most 2 children. Just as is observed, 20 is the parent of 2 other nodes, with a value of 6 and 52 on the left and right side respectively. Now let's extend our binary tree to see what is a full binary tree. A full binary tree is a binary tree in which all parent nodes or internal nodes have either 2 children or no children. In our illustration, all nodes except the leaf nodes have 2 children. And this is a full binary tree. But let's suppose that the node with the value of 11 has a left child. In this case, the condition for a full binary tree properties is not satisfied, and now this tree structure is not a full binary tree. And the next type is complete binary tree. A complete binary tree is a tree that is left justified and all levels are completely filled except possibly the last level. So in this case, the tree is not left justified because the node with a value of 14 must have its children first. And now the tree is left justified and all levels are completely filled except the last level. So this condition is also satisfied. And now the tree is a complete binary tree. Hello and welcome to this lecture. In this lecture, we are going to discuss about binary search tree. A binary search tree is a data structure that is an ordered tree, or in other words, we can say that it's a sorted tree. Why a sorted tree? Because all nodes on the left side are less than the parent node and root node, and all nodes on the right side are greater than parent and root node. As you can see, 6 on the left side is less than 20 and 52 on the right side is greater than 20. Let's extend our tree and check the new situation. In this case, the left child is less than 52 and right child is greater than 52. But as a subtree, all nodes on the right side must be greater than 20 that is located as root node. And the condition is not satisfied here because 11 is less than 20. Therefore, the structure is not a binary search tree anymore. But for instance, if we want to maintain the condition for the binary search tree, then we must replace the node with a value of 11 to something that is greater than 20 but less than 52. I prefer to choose 44. Now let's see how operations work on BST. The first operation is search. First, we will start by search operation. Suppose that the item that we want to find is 20. Then we must compare 20 with the root node. The root node has a value of 50 and 20 is less than 50. It means that we must skip right subtree and start searching for the item in the left subtree. Compare 20 with the next root node. 20 is greater than 15. It means that we must skip left subtree and we must traverse the right subtree because all items on the right side are greater than root. Compare 20 with the next item, and as we can see, item found. Now let's check how deletion works. Deletion has mainly three different cases. The first case is when the node to be deleted is a leaf node. Suppose we want to delete node with a value of 62. Simply, we can delete that without any further action. In the next case, suppose that the node to be deleted has a single child. In this case, we want to delete the node with a value of 65. This case is not complicated, and very simply we can move its child node as the parent node that was deleted. In third case, the node to be deleted has two children. Suppose we want to delete node with a value of 15. It has two children. In this special case, we must get the in-order traversal of the tree, then replace the node with its successor. If you know nothing about in-order traversal, then I highly recommend you to watch the lecture related to tree traversal that I have provided. And now in-order traversal of this tree is provided as is observed on the screen. So simply we must replace successor with the node that we want to delete. The node that we want to delete is 15, so its successor is 20. The next operation is insertion. Suppose we want to add 25. Compare 25 with a root node to find its correct path. 25 is less than 50. Then we must traverse the left subtree, because all elements on the left side are less than the root node. Compare 25 with 15, and as is observed, 25 is greater than 15, so it means we must traverse right side. Therefore, compare 25 with 20, and 25 is greater. So it means that we must add the node with a value of 25 to the right side of the node with a value of 20. Hello and welcome to the introduction lecture about heap data structure. In this lecture, we will talk about what heap is exactly. A heap data structure is a complete binary tree. So before I get into explaining what the heap data structure is, I must talk about complete binary tree. Therefore, what is a complete binary tree? A complete binary tree is a tree structure that have two main properties. The first is that all levels are completely filled except possibly the last level. And the next property for the complete binary tree is that the tree must be left justified, or in other words, the tree must be filled from left to right. As is observed, the child has been added to the left side of the leftmost node. Heap can be of two types. In fact, this complete binary tree can generate max heap if it satisfies two most important properties. The first is that when the value of the root node is maximum among all nodes, and the second property is when any given node is always greater or equal to its children. As is observed, 20 is greater than both child nodes, 18 is greater than 10 and 14, 15 is greater than 6 and 8, and 10 is greater than its child. Additionally, this complete binary tree can also generate a min heap when the value of the root node is minimum among all other nodes, and when the value of parent node is less than or equal to its child nodes. As is observed, the value of root node is minimum among all other nodes. And the next condition is that the value of any given node is less than or equal to its children. So 2 is less than its both children. 6 is less than 10 and 18. 8 is less than 22 and 25. And finally, 10 is less than 50. Hello and welcome to the lecture about array representation of heap. A heap data structure is typically represented as array. Basically, we will start by the root element that is at index 0, and the rest of the tree will go from left to right until filling all the values. There is a relationship between parent and child nodes, and we will see it in array structure. We will consider that which children belongs to which parent they have. The parent of each node is accessible via the formula that is given. For example, if we want to know which node is the parent of the node with the value of 8, then we must find its corresponding index, that is 6. The formula is I minus 1 divided by 2. I is equal to 6, that is the index of 8. It means 6 minus 1 divided by 2. 6 minus 1 is equal to 5, and 5 divided by 2 is 2.5, but we need its floor division. So 2 is the index of the parent. The node at index 2 indicates to 15. Let's discuss about another example. Suppose we want to get the parent of node with a value of 10 at index 3. I is equal to 3, then 3 minus 1 is equal to 2, and 2 divided by 2 is equal to 1. So the parent of the node with the index 3 and with the value of 10 will be at index 1 with the value of 18. The left child of any given node will be obtained by the formula that is 2 times I plus 1. For example, if we want to get the left child of the node at index 2 with the value of 15, then the left child will be obtained with the formula. So I is equal to 2, and 2 times 2 is equal to 4, and 4 plus 1 is equal to 5. Then the left child is at index 5 with a value of 6. So let's have another example. If we want to get the left child of the root node, I is equal to 0, and 2 times 0 is 0, and 0 plus 1 is equal to 1. So the left child will be at index 1 with the value of 18. And the last formula will return right child. Suppose we want to get the right child of 15 with index 2. 2 times 2 is equal to 4, and 4 plus 2 is equal to 6. It means that the right child is located at index 6 with the value of 8. Let's have another example. Suppose we want to get the right child of 6 that is at index 5. I is equal to 5, then the right child is located at 2 times 5 plus 2. That the result is equal to 12, but there is no such index, and it means that the node has no right children. Hello and welcome to the lecture about heap creation. In this session, you will learn about creating a heap, specifically a mux heap. The process is also the same for the creation of min heap instead of the tree structure that the root and parent node must be less than their child nodes. Let's get started by creating a heap from the given array. We must insert all nodes one by one, then compare them to previous node to maintain heap properties. First of all, suppose that the first element is already in the heap data structure. Accordingly, a node that is alone is a heap because there's no node to compare with. Additionally, when you have only one element in your heap, then you can also call it min heap or mux heap. Then go to the next step and insert second element to the left side of the first element. Now, because we decided to create a mux heap, then we must make sure that adding new element doesn't distort the properties of mux heap. In fact, the value of the newly added element must be less than or equal to its parent, that is 10. But not only with its parent, but also with all ancestors if present. In this case, because 20 is greater than 10, then we must swap them to maintain mux heap property. Go to the next step and insert the next element with the value 4. When adding next node, we can observe that 4 is less than the parent node. Then go to the next step and add the next item to the left side of the leftmost node. Add 15 to the left side of 10. Check if the newly added item has distorted maxi property or not. Yes, as you can see, it has distorted the maxi property because 15 as the left child is greater than its parent. Then swap them to maintain maxi properties and check whether 15 is greater than 20 or not. As is observed, 15 is not greater than 20. Then go to the next step and add the next item, that is 18. Add 18 to the right side of the 15 and check whether it is greater than its ancestors or not to maintain maxi properties. 18 is greater than 15, so swap them. However, 18 is not greater than 20. And finally, insert 9 and compare it with its ancestors, whether it has distorted maxi properties or not. 9 is greater than 4, then we must swap them to maintain maxi properties. But 9 is not greater than 20. This was all about top-down approach, and now let's to see how bottom-up approach works. Previous approach was based on top-down approach, and now we will discuss about another approach called bottom-up approach or heapify. Heapify is the process of rearranging a binary tree into a heap data structure. This is a process that we will take a subtree at the lowest level and then start checking whether this subtree follows heap property or not. Initially, we must create a complete binary tree from a given array. We only need to create our complete binary tree regardless of heap data structure properties. As you can remember, a complete binary tree is a tree that all levels are completely filled, except possibly the last level, and the tree must be left justified. So add nodes one by one from left to right to construct our binary tree. After constructing our binary tree, now we need to rearrange it to maintain heap data structure properties. In this structure, we will start by the last non-leaf node or rightmost node that has children, because we assume that all alone nodes are in our heap data structure, so we can skip 9, 18, and 15 and assume that they do not distort heap data structure properties. And specifically, we're talking about a max heap property for this example. Let's start by last non-leaf node and just have an overview from right to left to find a node with at least one child node. According to the formula given in the left box, the last non-leaf node will be the node with the value of 4. Heapify this node by checking its children, then the node with the value of 9 is greater than 4. Accordingly, you need to swap them to maintain max heap properties. As a subtree, this part maintains max heap data structure. Therefore, go to the next step and the next element will be 20. Check its children and choose the one that is greater to swap with 20, but none of them are greater than their parent. So this part and this subtree also maintains max heap data structure properties. Go to the last node and look downwards. Check whether its children are less than the parent or not. Among children, we must choose the one that is greater. 20 is greater than 9, then we must swap it with 10. Every time that there is a swap, then we must call heapify again. Now check whether 10 is greater than both child nodes. As you can see, 18 is greatest among children. Then we must swap it with 10. And now the heap condition is fulfilled. Hello and welcome to the lecture about heap operations and specifically deletion and insertion. We want to delete a node or insert a node into the heap while maintaining the heap properties. Suppose we want to delete the root node with a value of 2. Delete it and replace it with the last element from last level. As you can see, the last element or last node is the node with the value of 50. move it and place it as the root node. Now we must be careful because replace node may not follow the min heap property. Because this is a min heap, then any given node must be less than or equal to its children. So because the value of replace node as the parent node is greater than of its both child nodes, then we must swap it with the smallest item, that is 6, to maintain the heap property. Because 6 is less than 8, then we must swap it with 50. In other words, we must heapify the node that we put as the parent node. Again, 50 is greater than both child nodes. Then we must swap 22 with 50. And finally, 50 is at its correct position. Now let's see how we can delete a node from a mux heap. In this example, suppose we want to delete the node with the value of 22. As you can see, this is the node that we want to be removed. Remove it and then replace it with the last element from the last level. As is observed, the last element or last node is the node with a value of 4. Move it and place it at the index of the deleted node. Now we must be careful because replaced node may not follow the mux heap property. Because this is a mux heap, then any given node must be greater or equal to its children. So because the value of replaced node as the parent node is less than of its both child nodes, then we must swap it with the greatest one, that is 16, because 16 is greater than 14. In other words, we must heapify the last node that we put as the parent node. So that's all about a deletion process. Now let's have a look to insertion operation. The task is to insert a new element into the heap while maintaining the heap property. The idea is to first increase the heap size by 1 to store new item. Then we must store this new item at the end of the heap. Suppose we want to insert a node with the value of 4. Heapify this new element following a bottom-up approach because the new element may not follow heap properties. Since the heap data structure is a min heap, then the parent must be less than both child nodes. However, as you can see, the parent is not less than its right child. So we must swap them to maintain the min heap property. Then we must heapify it again. 4 is less than 8, then we must swap it with 8. And finally, 4 is greater than 2. Or in other words, 2 is less than its both child nodes. Now let's have an example for insertion operation in mux heap data structure. The task is to insert a new element into the heap while maintaining the heap properties. The idea is to first increase the heap size again by 1 to store new item. Then we must store this new item at the end of the heap. Suppose we want to insert a node with a value of 29. Heapify this new element following a bottom-up approach because the new element might distort the heap property. Since the heap structure is a mux heap, then the parent must be always greater than both child nodes. However, as you can see, the parent is not greater than its right child. Therefore, we must swap them to maintain the mux heap property. Then we must heapify it again. 29 is greater than 25. Then we must swap it with 25. And finally, 29 is less than 50. That is its parent. Then the structure follows mux heap property.